Okay, class. So in the previous video, we saw one shortcut of how to find the indefinite integral of functions that look like x to the p as long as p isn't equal to -1. Here, I want to show you two other properties of indefinite integrals that are going to be useful. And they're going to be similar to some we saw with derivatives. For example, if you want to take the integral, the indefinite integral of a constant times a function, you can move the constant outside, just as we do with derivatives. Second, if you have the indefinite integral of a sum of functions, well, we can just split it as the indefinite integral of one function plus the indefinite integral of the other function. Okay. For example, suppose I'm looking for the indefinite integral of 3x to the 4th plus 1/2 x to the 7th. Okay. By these properties here, I have a sum, so I can first separate this as a sum. So this would be the integral of 3x to the 4th dx. And never forget the dx. Again, right now it's kind of unclear why it's there. You have to keep to the notation, because again, there's a reason why it's there. Plus the indefinite integral of 1/2 x to the 7th dx by the sum rule, okay, by this. Now, by the constant multiple rule, I can forget about those constants, so I can just move them outside. Okay, so this equals 3 times the integral of x to the 4th dx plus 1/2 times the integral of x to the 7th dx. Now, I can go ahead and solve each of those separately. Okay. So by the previous theorem, what is the indefinite integral of x to the 4th? Well, we still have the 3 outside. Well, we know we just add 1 to the exponent and divide by that new exponent, and we have the plus c. That's the first part. For the second one, we can do the same trick, right? The same shortcut. Add 1 to the exponent, divide by the new exponent, and add c. Now, this is the answer, but we can simplify it one more step. Okay. So what is that more step? That one extra step. So let's go here. So here we can multiply the 3 out. Now, the thing that's going to be nice is that what is going to be 3 times c? C is an arbitrary constant. If you multiply an arbitrary constant by 3, you still have an arbitrary constant. What that means is that we can simplify this as 3 x to the 5th divided by 5 plus some arbitrary constant, right? Because 3 times an arbitrary constant is again just an arbitrary constant, plus 1/2. Okay, let me simplify that. Oh, let's just do it like this. So the 8th divided by 8. And again, 1/2 times an arbitrary constant is just an arbitrary constant. And then not only that, if I want to simplify this even more, if I have a constant that's arbitrary plus a constant that's arbitrary, well, that's just another constant that's arbitrary. So I can simplify this to be 3/5 x to the 5th plus, and I'm going to simplify the 1/2, so I'm going to multiply the 2 by the 8. So that's x to the 8th divided by 16. I can combine the two arbitrary constants to one single arbitrary constant. And then that's the answer, as simple as we can. And we see that this matches what we should get, because remember, when we're looking for something like this, it should look like what? Well, one specific antiderivative plus one arbitrary constant. So that's how we use this property here. Now, we're going to do another example that's a little bit more complicated, but it's still the same thing. And the idea is you want to use these two rules here to simplify your indefinite integral as much as possible before you try to find the antiderivative. Okay. So what do I mean by that? Before finding the one antiderivative of this and then adding the plus c, instead I'm going to use those properties. First, I can bring the 3 outside. And again, never forget the dx. Okay. What else can I do? Well, this is not going to be any property. I'm just going to simplify the inside. this, whenever you're subtracting on the top or adding, you can separate it as two fractions. It's going to be 2x to the 16th divided by x cubed minus x to the negative 7 divided by x cubed dx. Okay. So again, that wasn't any property, it's simplifying. Again, I'm just going to simplify, not use any property. We have x to the 16th on the top, 3 on the bottom, so that's x to the 13th. Oops. And then here we have negative 7 on the top, 3 on the bottom. So remember, when you're dividing, you subtract exponents, so that's x to the negative 10 dx. Now what am I going to do? Now I'm going to use the sum rule. I'm going to divide this as, okay, 3 on the outside, and I'm going to divide this integral here. So I'm going to divide it as the indefinite integral of 2x to the 13th dx minus the indefinite integral of x to the negative 10 dx. And again, I can do that by the sum property. I'm going to simplify that even more. Actually, I'm going to go to another page, okay, so I have more space. So right now I have this. I'm going to distribute the 3 out. Okay. Now, again, before I solve, I'm going to simplify as much as possible. I have an extra constant there, multiplying the function. I can move it out. So this is going to be 2 times 3 on the outside, 6. Integral of x to the negative to the 13 dx minus 3 integral of x to the negative 10 dx. And now I can go ahead and just simplify. Okay, find an antiderivative. So what is this? It's going to be 6 times, by the property that we saw in the previous or 2 videos ago, add 1 to the exponent, divide by that, add c, minus 3 times, okay, add 1 to the exponent, so negative 10 plus 1 is negative 9, divide by that new exponent, add c. Then the last thing, we can just simplify this, right? So you can multiply the 6 out, so it's 6x to the 14th over 14, minus, and again, I'm multiplying the 6 times the c, but that's just another arbitrary constant, minus 3 to the x to the negative 9, divided by negative 9. Again, I'm also multiplying the 3 by the c, but that's just a constant. I have an arbitrary constant plus an arbitrary constant. I just combine them to one arbitrary constant, c. And then that's the answer. That's the indefinite integral of that original function.